Assalamualaikum. My name is Anis Adriana binti Kamajuan and my matrix number is 2023472266. In this slide, I would like to explain about Teluk Aman Field Development based on a project overview. So, the location that chosen at offshore Terengganu in Peninsula Malaysia and the development well we chosen at well TA01, TA02 and TA03. The rig type that chosen is jack-up rig and the project objective on this slide to design a safe, efficient and cost-effective drilling program for offshore stack sandstone reservoir. Moreover, including well trajectory planning, casing and cementing design, drilling fluid selection and drilling risk mitigation. So next, I'll move on to the next slide. In this slide, I will explain for you about the field background and overview. So, based on the field background, Teluk Aman Field is a newly discovered offshore oil field located approximately 60 km in offshore Terengganu in Malaysia. The field is situated in a shallow water with an average water depth is about 180 feet, that making suitable for development using a jack-up rig for drilling a rig because of the jack-up rig used when the depth is less than 400 feet. Then the geological setting consists mainly of interpreted sandstone and shell formation, representing a classic shallow marine depositional environment. Moreover, based on the general drilling consideration, the formation generally provide a stable borehole condition. However, the presence of shell layer may lead to shell swelling and wellbore instability if inappropriate drilling fluid are used. Therefore, careful planning of drilling fluid selection and casing design is required during this field development.
Assalamualaikum. My name is Shafika Amalin binti Sobri. My matrix number is 2023491684. Alright, for this slide, we present the well target and coordinate using the northeasting system. Basically, we plan three directional development wells from one fixed jacket platform. So all wells are designed to reach the target reservoir in the Pasir Laut Formation. On the right side, the table shows the target coordinate for each well, including the total depth, northing and easting value. This coordinate system helps us define the horizontal displacement of each well from the platform, so we can plan the well trajectory accurately and ensure each well reach the correct reservoir target. So for this slide, explain the coordinate convention and the design rationale. In this northeast system, positive value represent the north and east direction, while negative value indicate south and west direction. From the 3D view shown here, we can see the well are deviated in different direction to reach different target. So this design is important because it improves well spacing and reservoir coverage. At the same time, drilling multiple wells from one platform reduces the surface footprint and also lowers the overall development cost. So we're moving on to the spider plot. So this is the plan view of the three well drill from the same platform located at the origin, which is 00. So the plot used the northeastern coordinate system to show the direction and horizontal departure of each well. Then the main purpose of this spider plot is to confirm that well TA01 to TA03 are oriented in the different azimuth direction. So the well are properly spaced, and also this help us to reduce the risk of the well collision and ensure better reservoir drainage across the field. So for the well trajectory design, we apply a build and hold profile, also known as a J-type trajectory. The well starts vertically and then begins building angle after the kick-off point or KOP. After that, the well holds a constant inclination until it reaches the target reservoir. So for this type of trajectory, is selected because it is efficient and stable with smoother curvature and lower dog leg severity. So it also helps reduce drilling risk and make casing running and cementing operation easier. So from the plot on the right, we can see the trajectory profile for well TA01, TA02, and also TA03, where each well reach a different target departure while maintaining a controlled and consistent path.
So let's move on to the next slide based on a casing program based on casing size and hole section. So in the Teluk Aman drilling program apply for casing string to ensure wellbore integrity and safe drilling. So the casing chosen is conductor casing, surface casing, intermediate casing, and production casing. As you can see, the plain hole size versus casing size at your right. So we choose surface casing. For surface casing, the hole size uh, 17.5 inch and the casing size is 13.375. So in this selection, we consider because of the isolate shallow weak formation and protect shallow zone. Moreover, to reduce risk of shallow hole instability during drilling. Next, we move on to the intermediate casing. The hole size that our group chosen, uh, 12.25, and the casing size is 9.625. So in this intermediate casing, we consider because of the cover, the mid section where the PPFG, pore pressure fracture gradient, margin become narrow, and moreover, it helped to improve wellbore stability and reduce kick and loss risk. Next, for the production casing, we use 8.5 inch for the hole selection, and the casing size we use 7 inch. In this selection, we consider to isolate the stack sandstone reservoir, reservoir X and reservoir Y. So it enable safe for long-term production and injection operation. As you can see, the conductor casing that we chosen is 18 5.5/8 at depth 150 feet. That is, we chosen that range of size because of the conductor casing. It provide shallow structural support and stabilize unconsolidated near surface sediment. It acts as a foundation for drilling operation and prevent shallow washout. So next, let's continue to the casing program based on the size and hole section. We consider the design consideration based on the casing program is designed to mitigate key challenge. First is shell swelling and dispersion at upper hole. Next, differential sticking risk at sandstone interval, and moreover at narrow pro pressure fracture gradient window at mid section.
Assalamualaikum, my name is Nuraida Nasira and my matrix number is 2023388243. In this slide, I will explain the pore pressure and fracture gradient chart. For the Teluk Aman field, establishing a safe drilling window is paramount due to the slightly overpressured nature of this clastic formation. Looking at the chart, the primary lines you see are the pore pressure line and the fracture gradient line. The pore pressure line represents our lower limit. If our mud weight falls below this line, we risk a kick or fluid influx because the formation pressure exceeds the hydrostatic pressure of the mud. The fracture gradient line represents our upper limit. If our mud weight exceeds this, we risk fracturing the formation and losing circulation. Based on the field data, the Teluk Aman field is slightly overpressured. As we drill deeper, the pressure increases from 220 psi at 500 feet to a maximum of 6,600 psi at 10,500 feet. For our specific wells, this means that TA01 targets a depth of 8,400 feet with a pressure of approximately 5,400 feet. TA02 and TA03 are deeper, reaching targets near 10,000 feet with pressures exceeding 6,100 psi. The space between these two lines is our safe mud weight window. Our goal is to maintain a mud weight that provides enough overbalance to prevent shale swelling, a known hazard in this field, without being so heavy that it fractures the sandstone reservoir. The vertical and horizontal dashed lines on the chart represents our casing setting depths and kick tolerance checks. We have placed the surface casing at 700 feet and intermediate casing at 4,500 feet. These depths were chosen specifically where the PBFG margin becomes the narrowest. The kick tolerance line in yellow and the annulus pressure profile verify that even if a kick occurs, the pressure exerted at the casing shoe will stay below the fracture gradient line. This slide details our final casing setting depth in true vertical depth and the engineering rationale behind these decisions. For our phase 1 campaign at Teluk Aman, we have standardized a 3-string casing design across all 3 wells to ensure consistency and safety. Our surface casing is set at 700 feet for TA01, TA02 and slightly shallower at 600 feet for TA03. For intermediate casing, these shoes are placed between 4,100 feet and 4,500 feet, depending on the specific well trajectory and local pressure regime. As for production casing, in all 3 wells, this string is run to the total depth of the well to fully line the reservoir intervals. Our selection of these specific depths is driven by 2 main operational goals. First, the surface casing shoe is designed to stabilize the shallow, unconsolidated formations. By setting it at these depths, we minimize the risk of well bore washout and provide a solid foundation for the blowout preventer. Second, the intermediate casing shoe is our primary defense against pressure fluctuations. As we saw in the PPFG chart, the margin between pore pressure and fracture gradient begins to narrow significantly in the midsections. We have intentionally placed the intermediate shoe just in advance of this narrowing to mitigate the risk of taking a kick or suffering circulation losses. The production casing is run to the bottom of the hole, reaching 8,400 feet for TA01 and up to 10,000 feet for TA02. This string is critical because it isolates the targeted Pasir Laut sandstone reservoir. By lining the entire interval, we ensure that the stacked reservoir, reservoir X and Y, can be operated safely and over the long term without the risk of cross-flow or formation collapse.
This graph presents the endless pressure profile for well TA01 during a kit scenario control. That is shown on the vertical axis in feet and pressure on the horizontal axis in PSI. The blue line indicates the pore pressure, the natural pressure within formation, while the red line represents the fracture gradient, the pressure at which the formation will fracture. The region between the two lines defines the safe drilling window. The dash kick tolerance line illustrates the annulus pressure when circulating out 15 barrels gas kick. Importantly, this line remains safely below the fracture gradient at the casing shoe depth, around 4,500 feet, confirming that the intermediate casing shoe is set in a formation strong enough to withstand a kick without inducing lost circulation. Kick tolerance analysis addresses a vital safety question. Can the well withstand a kick without fracturing the formation at the casing shoe? Based on our calculation, And the assumption is a key volume of 15 barrels and over balance of 100 psi and gas gradient of 0.1 psi per foot. The outputs from our SL shows and analyze that provided the key tolerance lines plotted on the PPFG chart, the analyze profiles during key circulation and the surface pressure after key evacuation. So, the engineering objective is to verify that during a kick event, the pressure at the casing shoe does not exceed the fracture gradient, thereby maintaining well control and preventing loss circulation. Also that this analysis directly informed and validated our decisions regarding the intermediate casing setting depth and the mark weight safety margin. Finally, we conducted a casing strength to check verification structural integrity against collapse, burst, and tensile loads during drill and well-controlled operation. For the surface casing, the calculated collapse loads were approximately 167 psi, which is well below the collapse rating of grades like J55 or H40. The burst loads were around 1,720 psi, also safely within the burst rating of approximately 3,000 psi. All the three wells TA01, TA02, and TA03 passed the collapse and burst checks for the surface casing. For the intermediate casing, collapse loads range from 2,450 to 2,366 psi, and the burst loads were between 2,236 and 3,070 psi. Even under this high pressure, stronger casing grades such as LAT and NLAT provided a sufficient safety margin, and all wells passed. Tension checks were also certified, as the casing tensile rating as its self-weight load when the appropriate safety factor is applied. In summary, the surface casing utilizes credit like H40, JT5, or K55, which are safe for the expected loads, while the intermediate casing employs higher strength grades like LT or NAT to handle greater depths and pressures. All the casing strengths meet the required safety standard with the adequate margin.
This section covers the cementing program and TOC estimation for the Teluk Aman field development. The primary purposes of cementing are to achieve zonal isolation and prevent fluid movement behind the casing, to support the casing strength and enhance well stability, and to ensure safety during drilling and the long-term functionality of the well. For our surface casing, we are using a slurry design based on Class AB cement with a 6% bentonite additive. The design slurry density is 13.49 pounds per gallon with an excess factor of 1.3. The total job will require approximately 337 sacks of cement and over 3,000 gallons of mixing water. For the intermediate casing, we step up to Class D cement again with 6% bentonite. This slurry is slightly denser at 13.63 pounds per gallon. For this section, we estimate needing about 328 sacks of cement and just under 3,000 gallons of water. These designs are tailored to the specific pressures and formation of Teluk Aman field, which consists of interbedded sandstones and shells. The goal is to ensure a complete, competent cement sheet that provides permanent zonal isolation across our target reservoirs in the Pasir formation, safeguarding the well's integrity for its entire life cycle. Next, we'll compare two casing design strategies for the Teluk Aman wells, focusing on well control risk and economics. We are analyzing the intermediate casing designs for well TA01 and the deeper well TA03. The key difference is driven by depth. Well TA03 being significantly deeper encounters higher formation pore pressure. This directly translates to a greater demand on the casing's ability to withstand internal pressure or its burst rating. While both well designs successfully pass the required stress checks for collapse and burst using standard grades like L80 or N80, the conditions for TA03 are more critical. The elevated pore pressure in TA03 increases the inherent risk of a burst load scenario. Therefore, its design requires more careful validation and potentially a higher grade casing specification to ensure the safety margin as the shallower well. In summary, deeper wells like TA03 dictate a more robust and critical evaluated casing design due to increased pressure-related risk, which is a primary factor in both well safety and overall project economics. Let's examine the mechanical load analysis for well TA03 compared to well TA01, focusing on both collapse and burst loads. First, looking at collapse loads, which is the external pressure trying to crush the casing. For the deeper well TA03, the collapse pressure is significantly higher due to increased overburden and formation pressure at depth. The design envelope shows that the casing must withstand higher external forces, especially at the shoe depth compared to the shallower TA01. Second, burst load, which is internal pressure trying to rupture the casing. Well TA03 faces a more severe challenge. The higher pore pressure at greater depth creates a much steeper burst pressure profile. The casing, especially in the surface and intermediate sections, must be rated to contain these higher internal pressures without failure. While both wells are designed with safety factors in mind, TA03 operates much closer to its mechanical limits for both collapse and burst. This confirms that deeper wells require stronger, higher grade casing, more rigorous design validation, and often results in higher material and operational costs. In summary, depth drives both external and internal load risks, making TA03 the more critical design case for ensuring well integrity and cost-effective construction.
To conclude our technical proposal, we present a final recommendation for the Teluk Aman Phase 1 drilling campaign. This section synthesizes our casing design and setting depth strategy into a single executable program. Based on our analysis of the clastic sequences and pressure regimes, we have selected 4-string casing. For the conductor string, a 24-inch hole will be drilled to set the 18 and 5.8-inch casing at 150 feet. Surface string, a 17.5-inch hole for a 13 and 3/8-inch casing. Intermediate string, a 12.25-inch hole for a 9 and 5/8-inch casing. Production string, 5 and 8.5-inch hole will be drilled to run a 7-inch casing to the total depth. Our shoe depths are tailored to the specific target depth of each well to ensure maximum mechanical integrity. For TA01, a surface casing at 700 feet and intermediate at 4,500 feet, reaching a total depth of 8,400 feet. For TA02, the surface casing is set at 700 feet and intermediate at 4,200 feet, reaching our deepest total depth of 10,000 feet. As for TA03, a slightly shallower program with surface at 600 feet and intermediate at 4,100 feet, ending at 9,800 feet total depth. Our recommendation is backed by 3 critical engineering checks that ensure the safety of this program. The PPFG margin, where all casing setting depths were selected based on our pore pressure and fracture gradient analysis to maintain a safe operational window. As for the kick tolerance, the outcome of our kick tolerance test proves that these casing shoes can successfully cope with anticipated kick conditions without reaching the formation fracture pressure. And finally, for the structural integrity, comprehensive checks for collapse and burst pressure demonstrate that all casing strings across all sizes meet the required strength standards for the expected bottom hole pressure of up to 6,600 psi.